So this is problem C2, not so simple polygon embedding, from the Educational Code Forces round 87, which is also the Harbor Space University round. I think it was actually sponsored by them. So there's actually two problems. One is problem C1, which is called simple polygon embedding, and then there's problem C2, which is not so simple polygon embedding. And my Wi-Fi just shut down, which is great. Um, But so the main thing here is that the difference is that in C1, n is always even, and in C2, n is always odd. Now I'm solving C2 because C1 is quite simple, and I'll show why that is shortly. But I'm solving C2 here because it's a little bit more tricky. And you might notice I actually have another tab open here. We'll get to that later, but first let's read the problem. So the statement of this problem is the same as that of C1, except C1 n is always even, and in C2 n is always odd. You are given a regular polygon with 2 times n vertices, and all of its sides have length 1. Now, if you don't know basic math, you probably want to do that. In fact, this is going to require you to know a lot of math. This is also going to require some trig. I don't actually know how to do trig in C++, so that's going to be fun. We're going to figure out how to do that. But there probably should be some way to find cosines and sines and stuff like that. And we can build the rest of the trig that we need from that. But anyways, your task is to find the square of minimum size such that you can embed a 2n-gon in the square. Embedding means you need to place the 2n-gon in the square in such a way that each point lies inside or on the border of the 2n-gon. And this is a little bit of a grammatical error, or my brain is just not working, but you need to place the 2n-gon in the square in such a way that each point which lies inside or on a border of the 2n-gon should also lie inside or on a border of the square. Basically, you need to inscribe it. You can rotate the 2n-gon and or the square. Now, we're going to not rotate the 2n-gon. Well, we might actually rotate the 2n-gon. I don't think we will, but what we'll be doing is we'll rotate the square. I'll have to check the other tab to tell, but for the time being, let's continue. The first line contains a single integer t, which is the number of test cases, and the next t lines contain in each test case, which contains a single odd integer from 3 to 199. And you need to embed the 2n-gon, not an n-gon. An n-gon, which is odd, would be incredibly hard to embed, but a 2n-gon is a little bit easier. Obviously, it's harder than a purely even one, which is divisible by 4, but we actually can't determine anything from the test case here because there's no reasoning why or how or any stuff like that. But what we can do is use some computer-assisted design for a very simple purpose. So this is called OnShape. OnShape is something I think is a very useful tool for computer-assisted design, and you can use it for assisting you with math or things like that. Obviously, don't use this in a mathematical contest because that's kind of cheating, but when you're just solving some math problems on your own and you need to figure out some stuff, it's pretty similar to GeoGebra. I just prefer this because it has a lot more power with it than GeoGebra. But if you prefer using GeoGebra, you can also use that too. It's pretty much the same thing. So what we've done here is what we've done here is we've actually gotten up the problem statement for n equals 5. Now, let me quickly, and this is one of the reasons why I said it's actually incredibly powerful. Right. So let me quickly show you how I kind of got this. So we'll keep this on the side as a reference, but for the time being, we're not going to include that. So the first thing you're going to need to do is choose center point circle, and we're going to need to draw a circle. And the reason is OnShape only allows you to do inscribed polygons or circumscribed polygons. Inscribed polygon, actually, these don't actually make much sense. Inscribed polygon means the circle is inscribed inside the polygon. It's very confusing. So what we're going to do is we're going to do this. We're going to kind of align it like this. It's going to be tangent, and You can hit escape for the time being. Oh, you don't want to hit escape, sorry. You want to hit enter for the time being. We'll fix the number of sides later. So what we'll do is you can choose 6, and actually 6 is a pretty good place to start. So for the time being, we're just going to rotate this. Well, actually, no, we're not going to rotate this. We're first going to move this center right over here. Let's move it right there. That seems like a good place to move it. And we're going to set the sides to a specific length. And so for that, you need to use the dimension tool. Now, the sides, they said were length 1. So we're going to set the sides to length 1, and immediately you can see now this is a lot smaller. Next thing we're going to need to do is we're going to need to just draw a random rectangle, and we're going to use the equals tool to turn this into a square. So we're going to use these two, and now it's a square. The next thing you need to do is use the coincident tool to make these two coincident and these two coincident. And obviously, not everything's contained in the square, inside the hexagon, but you might be able to, just shift this around a bit, maybe like that, and now everything's contained. Okay, so that has a length of 2.0, but the answer is 1.93. So where are we going wrong? After a bit of experimenting, you might actually figure out if we move this point onto here and this point onto here, OnShape will actually do some pretty cool things. So what you want to do is go back, use the coincident tool, and click this, and then click this, and this. And now OnShape is going to rotate that hexagon. And actually rotate it in such a way that now this is perfectly enclosed. There's no way we can enclose it more, because otherwise one of these points would have to reach outside. And now, if you take a look at the dimensions of the square, which you can find down here, it's 1.932, which is exactly what they have here. They just have it to a larger precision. So that's pretty cool. And OnShape has actually helped us figure out the correct answer. Now, if you wanted to, you could try and figure out this same thing for a larger, more, I guess you would call it a larger value of n. And so I drew a value of n as 5 right here. So take a minute and figure out take a minute and see if you can do the same thing. The steps right here are pretty much identical. The only thing you need to change is this from 6 to 8. And you'll also need to change some other things. But also notice my choices of where the points are touching this square. So hopefully you took some time to figure out why I chose the points the way I did. I actually made it coincident. So first things first, I made the coincident right here on these two. And so that's the first part. It's the same as these two coincident. But then the other thing I did is I chose these two. Now, you might be wondering why I didn't choose these two. And if you look at it, it should become immediately apparent to you. These two are the outermost, what you would call outermost points. You could have also chosen these two, but that's just the same. You want to choose the ones which are the defining points. The defining points are basically, imagine that we were to consider just half a square. If we were to just choose this half of the square right here, just this half, and this is actually half because it passes through the center of the square, then we would have kind of a 1, 2, 3, 4, 5. And that's because it's half of the polygon. It's gonna have 5 sides. So that's a lot of honking. What we want is we're going to say that obviously these points are the ones which are going to be the largest. Now we don't want to coincident this side to this side, because that's not actually going to be a square. That's going to be a little less than a square. We want to coincident it to the points. And by coincidenting it to the points, we actually, if you'll see this is for 5, you get 3.196. 3.1962261. That's exactly what we had right here. 227 is the and OnShape just has a maximum accuracy it can do. But now the next thing we need to figure out is rendering compatibility. But the next thing we need to do is okay, well OnShape figured this out. How do we figure it out? So what I've noticed here is that whenever you're considering just half of the square, and I'll show you what I mean on this side too. If I were to just put this through here, and that's going to be 2. So whenever you're considering half of the square, one of the basically this is going to be 2 and this is going to be 3. So you're going to have it split into an even and then an odd. And same thing here, even and then an odd. And you'll notice they're exactly 1 apart. That's because this point right here is going to be as close to halfway as possible. And that's because these 2 points are identical. We're basically choosing one of the points that's closest to halfway as possible because that's the point that's going to be the largest, the farthest away from the center towards the square, right? So we're going to choose this point. This should make intuitive sense to you why this is as close to half as possible. If you want, you can choose to rigorously prove this. I'm not going to because this is a YouTube video. But now that we know that, we can simply choose, well, which one has an even, and I'll explain why we're choosing that later. So for example, this one has even, it has 2, and it's going to be the shorter of the 2. It's going to be 2 versus 3, and we're going to choose even, which is 1, which is 2. And here we have 2 versus 1, we're going to choose the even one, which is 2, which is the larger one. So it doesn't matter if it's larger or shorter, we're going to want to choose the even one. And that's just going to make our calculations a little bit simpler. The next thing we want to do is we want to bisect that. And by bisecting that value, that even number of sides, we bisect it straight towards the other, one of the vertices of a square. And we actually bisect the angle of that square. Now, how do I know we bisect the... I'm pretty sure we bisect the angle of the square, actually. So there's a simple way I think we can figure that out, and that's just to use OnShape to determine that. So I'm going to choose this, and then this. That's 45 degrees. We're definitely bisecting that. We bisect the angle of the square, and so this is another way that OnShape can just help you figure out these small little things that you'll need. Now that we know that we bisect the square, we know that this angle right here is 45 degrees. This angle right here is 45 degrees. We can actually easily figure out this angle as well. This angle right here, it's just going to be, well, what's the even divided by 2? So we have the even as 2. So out of the 5 that are right here, we're choosing 2 of the sectors. We're choosing 2 of the angles. So if we were to divide each, like draw each of these lines, and actually let's do that. If we were to draw each of these lines, and this is going to start to get a little bit clustered. And what I mean by clustered is it's going to be a little bit hard to see, so at any time if you feel you need to pause, do pause and consider exactly what's going on here. So what you'll notice is that each of these angles is going to be the same since this is a regular polygon. What that means is each of these angles is going to have the same angle measurement, so each of these angles is going to be 180 over n. And since we're choosing the even value, we can simply choose 2 times 180 over n. And the same thing would happen here. If we had, for example, say we had n be 7, then we would be choosing 4 of the n, or 4 times 180 over n. So that would be that angle, and then we divide that by 2. Divide that by 2, and that would give us 2 times 180 over 7, or 1 times 180 over 5, or 1 times 180 over 3. If we had n equals 9, pause the video and think about this yourself. What exactly would our angle be? Well, if we had 9, what we would get is, that would be, well, you have 4 and 5, right? You split it into 4 and 5. So you would have 4 times 180 over 9, divide that by 2, would be 2 times 180 over 9. So hopefully you can figure out a formula there, and I'm going to actually pull up a notepad to explain this right here. So first things first, we'll calculate this angle right here, and that's just going to be, and suppose we know that what n is, we'll say it's going to be even of n, and I'm going to define e of n to be is equal to n over 2 if n over 2 is even, else n over 2 plus 1. And this is using floor division. Then what we'll see is we know that angle is going to be e of n times 180 over 9 times 180 over n, actually. All of this over 2. And to simplify this, we could actually make this 90. So e of n times 90 over n is equal to the angle. And now we have the angle right here. We have this angle. Now I've already given you a bit of help. This line that I've drawn is perpendicular to this line. So see if you can figure out, and this is assuming you know trigonometry, so see if you can figure out how we can calculate this right here, from here to here. So from here, see if you can figure out how we can calculate the distance between those 2 points. Well, this angle right here is 45. So we know that the distance from this to this is going to be the same as the distance from this, and I'm actually going to clear them all. The distance from this to this is going to be the same as the distance from this to this. And we can easily calculate the distance from this to this using the cosine of this times this. Or rather, the cosine of angle times radius. So then the other thing we need is to calculate this right here, this value right here, and that's simply the sine of angle times radius. So how do we calculate radius? Well, we can easily calculate radius since we know that right here, this is 1. We know this is 1, so we can easily calculate radius, again, using trig. Pause the video and see if you can figure out how we can calculate the radius using trig. Alright, so hopefully you paused the video and thought about it yourself. What we're going to do is first we're going to calculate this angle, and we already can calculate that angle to be 180 over n. So we know that set this to A2. Now what we can do is we can find this angle. Once we found this angle, we'll divide it by 2. So we'll say A2 divided by equals 2. And that will give us, and to make this a little bit more clear, I'm going to work on this diagram just for the purpose of showing that. We'll put this here, and we'll make sure that these are perpendicular. Since this is isosceles, we can assume that that's how it is. So we take this angle right here, that's the new A2, and we can find the cosine of it. Now, I mean the sine of it. Now, sine of this is equal to this from right here to right here, so the distance between these 2 points, which is just going to be half over the distance of these 2 points. So what I mean is, sine of A2 is going to be equal to 0.5 over radius. In other words, radius is equal to 1 over 2 times sine of A2. And again, calculating sines and cosines will hopefully C++ has a package or some form of include that allows us to do this. So here's a little bit of work that we can use to figure out exactly what this distance is. The distance from that to that. But how does that help us? Well, we can again use 45-degree angles. If we were to drop a perpendicular from this to this, that would form us a 45, 45, 90 triangle. Or another way you can visualize it is extend this past this to this point, right there, and that would give us the diagonal of the square. And once you have the diagonal of the square, you can pretty easily find out the side length of the square. So what we'll just do is we'll say, once we've got this distance to this distance, so basically the distance between the two yellow points, just multiply it by square root of 2, and that's our answer. So our answer is equal to this value plus this value times the square root of 2. And that's pretty much it. So what are the things we're looking for here? We're looking for number 1, we need a cosine. Number 2, we need a sine. And number 3, a square root. So trig in C++. So trigonometric to illustrate C++ functions. So we can just include math.h. I think with bits slash std, bits slash std c++.h, we should have math.h included. However, it's in radians and not degrees. So that's a little bit confusing. And actually not confusing, that's not good, because we can't calculate stuff in radians. We need degrees. So what we'll say is trig in C++ degrees. C++ trig functions in degrees. So what we'll do is we'll actually custom define some cosines, and sines, because it apparently we actually don't have cosine and sine of degrees. But that's okay. So the first thing we're gonna do, actually we don't need that. Let's pull this up and pull this up. So the first thing we're gonna do is say NSSPE.cpp. And that's a huge name, but it's fine. And we'll say def and MSIO, because we've got test cases, so we're going to need that. And we're actually going to define, and I think we actually have to define this up here to use it. We're going to define double secos of double angle, and I'm going to put D just to clarify that it's degrees. So what we're going to do is we're going to say, first, do we have pi? we're going to say angle is equal to angle. No, angle is equal to angle times equals no, d angle times equals m pi. D angle divided by equals 180. Forgot the semicolons. And 180d, that should be double value, I think. And now we simply have to return cosine of the angle. And now we'll just copy this and say c sine of double the angle and return sine. And so now we have our custom sine, custom cosine of m pi defined there. M pi we actually didn't need to define. So the next thing that we're going to do is get started with our work. So the first thing, well, now we need to get en. So we'll say int n sin n. And we'll say double en is equal to n over 2 n over 2 percent 2 is equal to 0, then n over 2 right. And that should give us our double. I have a feeling it's not gonna compile, and I don't know why. Next, we're gonna define double angle is equal to en times 90 d over double n. So we've got our angle. Now we need to calculate our radius. So double a2 is equal to 90 so let me think about this. Yeah, 90 d over double n. Yeah, this ternary operation, this is not going to work. So I'm going to say is equal to 0 if n over 2 percent 2. Yeah, that should work a bit better. So we got 90d double n And then we'll say double rad is equal to 1 over 1d over 2d times c sine of a2. And now we have a huge thing, so we're going to say double ans is equal to c cos of angle times rad plus c sine of angle times rad times square root of 2d. Sout and slash. And now we can cd dot dot, and we're basically just gonna cd into our file. So g++ minus std equals c++ 11 minus wall minus o2 and nsspe does cpp minus l nsspe. Alright. Convert into double. Alright, we probably could just do AD.0. Because honestly, that would work, like, pretty fine. Because apparently you can't use dot. You can't use D. Or maybe you can use D and I'm missing something. Math.h. It says pi should be defined. Well, if it's not, we'll do this. We'll need to reopen this. What we can just do is define my pi as this, my pi, and my pi. Because apparently it's not defined in scope. Then dot slash nsspe, and let's copy this and paste. 1.93185. What is Sout precision double? Yep, I think we're gonna have to do Sout precision as 7. Let's take it to 10. let's not do that. Let's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I think 20 should work. Okay, great. So that's it. We've actually pretty much finished it, and this is really nice because it works in, well, it works in the time complexity of cosine. So this is OT log t. Yeah, this should definitely work. So we'll choose our file. That's not at all what our file is. And SSP does. Alright. And fingers crossed, accepted in 31 milliseconds. Alright, so we've got C2 finished, C1 finished, and both of these, they ran in a pretty simple time, although they did take 12 minutes apart, partly due to my stupidity. But yeah, that's pretty much it. If you guys did enjoy, please don't forget to like and subscribe, and I'll catch you all in another video. And before I stop this video, here are the two pieces of code that we used for this, and I'm going to ignore those. So this is basically the main things that we used rather for this code. So here you go. And I will catch you all in another video.